Welcome back. I think this is the fourth video I'm recording today on energy, and I'd finished the last one with the question about how would we measure the energy change if we were burning a fuel, enthalpy of combustion we call it. And I said we use this apparatus. Before I get into this apparatus, let's go back and discuss this apparatus. That one. That was the one where I talked about neutralization. And I want you to think, where is the heat energy change actually happening? And it's happening inside the chemicals that are inside the coffee cup calorimeter. If the chemicals are changing energy inside, like energy is given out, then it's given out in there. And all of the energy that's given out kind of warms up the water that's inside that coffee cup. And therefore, that's why those experiments are good. I want you to contrast that with today's experiment, which is not going to be good. We know it's not going to be good. So let's fast forward to this apparatus. We use a metal can, and the metal can we're going to use is copper. So copper metal, you might call it a copper beaker, and we're going to put a burner, and I want to actually burn and get results for propanol. Now I don't normally I want to burn some propanol. I know that normally ethanol is used, but I wanted to vary a bit, and I've got, from the cupboard, I picked up some propanol, and we're going to work out how much energy is given out when we burn 1 mole of propanol in that apparatus. So the propanol is going to be in there. We're going to burn it. I'm going to warm up some water. The water's here. And remember, we're going to use the specific heat capacity of water to measure the temperature rise and use the specific heat capacity of water with the temperature rise and the quantity of water present to work out an energy change. That energy change we're going to scale up to a mole of ethanol burning. Now, what's bad about this experiment is the energy given out is here. It's at the flame. And the flame is not inside the water, is it? The heat energy here has to go up through the metal into the water. Can you see why that's not immediately going to happen, is it? We are going to get heat loss. The main thing wrong with this experiment is heat loss. Exam boards are always asking about it. They give you the experiment, you do calculations, they say what's wrong with the experiment? Heat loss. The heat given out by the fuel burning does not all go into the water. Most of it will be lost around the sides. And you can feel it with your hands if you put hands there. Most of it is lost around the sides. So I want you to understand that so you can answer those questions that happen. Let me show you the apparatus and let's do the experiment. So this is the apparatus. This is a spirit burner. It has a lid. I'm going to light the wick when I'm ready, but we'll keep the lid on to stop evaporation of the alcohol that's in there. Can you see it says on it propan 1-ol. Now I can draw that on the board, but you should be able to do it after the organic topic. You should be able to draw propan 1-ol. It's an alcohol, and I'm going to burn it, and that's a spirit burner. Now this is the thermometer, blue fill thermometer. At the moment it reads 17 degrees. And this is the copper can. Copper can, got nothing inside, made of copper. It's a bit black on the outside because we've done experiments where soot has collected and made it go black. So I'm going to put some water. I'm going to get 100 millilitres of water. I'm going to measure a volume. 100 millilitres of water. Into the metal can, and then I want to burn this here. Now, as you'll see, I've got a balance here. So let me just show you the balance reading. You can see it reads 0. When I put the spirit burner on, now it reads 228.90. 228.90. To 8.90 grams. 2 to 8.90 grams. Sorry, that doesn't go there, because that is mass of the water. So, mass of the burner, lid and propane one on was that much. I'm going to burn it. When I burn it, I'm going to write the final mass here. Then I'm going to subtract to get the mass of the alcohol burned. Right, let's show you how we do that now. So, matches, thermometer goes in to the water. Initially, that thermometer, get a piece of paper, that thermometer reads 19 degrees Celsius. 19 degrees Celsius, and then I'm ready to light the burner. Get my matches. We light the burner. And you should see, as the alcohol burns, the mass will go down. I hope you can see the mass going down. And the temperature will go up. That's probably a bit harder to show you. Now what I like to do is to keep the experiment going until I get a temperature rise of around 25-30 degrees. When I get the temperature rise of 25-30 degrees, I'm going to take the temperature and stop the experiment. I'm going to stop the experiment by putting the lid on that spirit burner. Well, it's coming to about 40 degrees, so it's gone up 21 degrees. And then I can't see the thermometer because it's not coming out. It is now. Right, now I can see it again. It's about 43 degrees. So I'm going to stop it before it gets to 50. 45 degrees. 46 degrees. 47 degrees, 48 degrees. There, I'm going to stop it. Stopped it. The temperature's still going up. It's now 50 degrees. I hope you can see the temperature. I need to be there where that stand was. So 51.2 degrees. 51.2 degrees Celsius. That's the final temperature. And how much does it now weigh? Well, 228.14. Sorry, 228.11, 228.13, 228.12. I'm going to take it as 228.12, 228.12. And let's have a look at the results that we need to do the calculation, and what we need are those results. I've got them here. So initially the mass of the spirit burner was that much. Finally the mass of the spirit burner was 228.12. Mass of propane 1 all burned. 10 take away 2 is 8. 8 take away 1 is 7. And these are 0, 0, 0. So the answer, 0.78 grams was burned. And the other thing I want to do while I've got you here is I want to talk about how many moles were burned. If we've got that many grams, how do we work out how many moles were burned? Well, you need the MR of propane 1O. This is propane 1O. The MR is 3 carbons are 36, 8 hydrogens are 8, and 1 oxygen is 16. Added together makes 60. So that is the MR of propane 1O. And if I've got 0.78 grams, I have to divide by 60 to get how many moles of it. And I need a calculator to do that. Mass of water. What mass of water did we have? Well, we took 100 mils, 100 centimetre cubes. Each mil, each centimetre cube is 1 gram. Everyone knows the density of water is 1 gram per centimetre cubed. So if I took 100, the mass would be 100 grams. Now, they are the results I need, and they are the results I'm going to do the calculation with, and I'm going to show you and carry on that calculation on my PowerPoint. So I'll pause it there and carry on PowerPoint. Carrying on then, that was the apparatus. We've got some results. I'm going to take you through the calculation. Remember, we'd said that these are the equations we're going to use. We need this one, the top one, we need that to work out the energy change in our experiment, and then we need the bottom equation to scale up to 1 mole. I'm going to do both of those things next. That was me explaining it to you in the previous video. So, the practical procedure, you saw me do it. You need to put a known mass of water in the beaker. You need to know mass of the chemical that burns, in this case propane 1O. You measure the temperature rise so that you can put those figures into that equation. All that I had on the board when I showed you. I've still got it on the board over there. But I've just transferred the figures into here a little bit more neatly. We had 100 grams of water because we had 100 centimetre cubes. We had that mass initially of the spirit burner. You saw on the balance, you saw the mass go down to 228.12. The mass of propane 1O that burned was therefore 0.78 grams, and it gave us this temperature rise of 32.2 degrees. Initially, The temperature was 19.0 degrees Celsius. I've missed out the degree Celsius. And 51.2 degrees Celsius. I missed out the degree Celsius. Mistake, forgive me on that one. I will forever be making little mistakes like that. But the temperature rise, if you subtract those, 32.2 degrees. So now with those results, I can put those results in to do a calculation. First, the energy change in the experiment. MC delta T is the energy change delta E. Delta E is not delta H. It's only delta H once you've scaled up and put whether it's positive or negative. Using the values I had, then delta E is 100, that's the mass of the water. Specific heat capacity of water per gram was 4.18. Change in temperature 32.2 degrees Celsius. Put those into a calculator, 13,459.66 joules. I rounded it to kilojoules. 1 kilojoule is 1,000 joules. So in thousands, the point goes there, 13.459, and I rounded it to 7. Now I haven't overly rounded, because if you overly round, say I round that to 13, then it will introduce a rounding error in the next bit of the calculation. I've not finished the calculation, so I don't want to round too early for introducing unnecessary errors. So this is the second part of the operation calculation, which is scaling up. Scaling up to burn what would have happened if we had a mole of propan-1-ol. Propane. I'm sorry, that's a mistake. I should say scaling up the burning of a mole of propan-1-ol. Sorry. Mass of propan-1-ol, that is propan-1-ol. Mass of it, 3 carbons, 8 hydrogens, 3 carbon 36, 8 hydrogen there are 8, 1 oxygen 16, add them all up, adds up to 60. So the moles of propanol burned will be my mass that I burn over 60. There. We had 0.78 grams burn. Divided by 60, you get 0.13 moles was actually burned. Now, to scale up to a mole, and then you call it delta H. Delta H will be delta E over moles. So that was my change in energy in the previous slide, value that I rounded, not overly rounded. This is my number of moles on this one. Divide the two, you get an answer of a minus. See the minus, you've got to have a minus. As soon as you start calling it delta H, I want you to stick a minus or a plus as appropriate. Minus means exothermic. In this, clearly exothermic reaction, energy was given out, so I need a minus. The value here was that much. Do it on your calculator. You find that it's 103.54 kilojoules per mole of propan-1-ol burned. The actual book value, if you look it up, theoretical, real answer, is minus 2010 kilojoules. What did we get? About 100 kilojoules. The actual answer is 2000 kilojoules. That is a very different answer that we got to the book answer. That's because these experiments are notorious for being rubbish experiments. If you wanted to work out an enthalpy change for burning a fuel, you wouldn't do it this way. If you look at the error is huge. Like 100 over 2000 times by 100 to get percentage, that's like 95% error. 5%. That is 5% of the real answer, roughly. Very high error. 95% error in this case. The high errors are due to heat loss, unsurprisingly, and the improvements would be put a lid on the metal beaker, put a burner inside a tall beaker to channel the heat up into the metal beaker, but those don't make much of a difference. They improve it a bit, and if you put them in an exam, they give you the marks. And that's why I'm mentioning them. they're the ones we normally put in an exam to improve the apparatus. But a far more successful way to improve the apparatus would be to calibrate the apparatus per degree. So you could burn a known alcohol in there, you know how much heat that gives off. If it made the temperature go up by 25 degrees, and you know that 25 degrees represented 25,000 kilojoules, then each degree is 1,000 kilojoules. What I mean is you can calibrate, and that would be a good way to make the same apparatus much, 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 much better. But if you do nothing, that apparatus is an appalling apparatus for doing calorimetry experiments. But you need to know it's appalling. You can't just say, oh, don't use it. It comes up on exam papers. You've got to talk about it intelligently. And the intelligent way to talk about it is to say, rubbish apparatus. Okay, so my next video, I think I'm going to stop this one on 21 minutes. My next video is about bond energies, really important. And this is a way of calculating any reaction. We're just going to use bond energies, which we can find in a data book. That's for next time. See you then.